So there's that gratuitous slide of Utah. Lots of nice Triassic and early Jurassic red sandstones. Warwickshire is of course nothing like that. Actually, you have to hunt for the outcrops. So this is Henley and Arden, the heart of Warwickshire, and that ridge is the ridge of the Arden Sandstone, and that's pretty much the type of exposure you get. So glorious green Warwickshire, you have to hunt around for outcrops. The type section of the Arden Sandstone is exposed on the Grand Union Canal. This is a photograph taken by the Canal and River Trust ecologists back in 2011 of the clearance work they did on the type section. We'll come back to this section later on in the talk. But much of the Arden Sandstone is exposed at that sort of level. There are the cuttings or the roadside cuttings or quarry cuttings, and they're hugely overgrown. So studying the Arden Sandstone in Warwickshire and the Midlands in general is a challenge. So the presentation, we're going to look at some context of the Mercia Mudstone Group and the Arden Sandstone across the UK. We'll think about the geological setting of the Mercia Mudstone Group, what it actually represents, and then we'll visit some Arden Sandstone outcrops in core and outcrops. We'll quickly look at some historical British Geological Survey data on paleocurrents and the distribution of the Arden Sandstone. And then we'll try and make an interpretation of what actually does the Arden Sandstone represent. Then we'll go and visit the Reverend Peter Brodie and his fossil finds. Some of those came from that canal cutting in Shrewley. And towards the end, I'll start arm waving and speculate and try and tell you what I think it all means. And that will include some modern analogues and some depositional models. And then we'll speculate a bit more wildly about Carnian climate change and dinosaur evolution. So that's the talk. So first of all, I'm going to set the scene for the Triassic, and I'm using some work done by Andy Newell at the BGS, published back in 2017. This is a delightful paper, and top right is a map of, it is a globe showing this supercontinent Pangaea. And Pangaea was the paleogeography of the Triassic, and all of the large continents that we know today were all fused together. And you can see that there was a large ocean, which we call Tethys, which is off to the southwest of Pangaea in this perspective. So you had a large ocean and then a supercontinent. If you can just make out the red star, that's approximately where Britain is. So back in the Triassic, Britain was in the middle of the supercontinent, and we know the climate throughout the Permian and Jurassic was actually quite extreme. Again, we'll come back to that later in the talk. And then bottom right, the view there is actually the paleogeography of Britain and Northern Europe. You can see the outline of the UK, Northern France. So the paleogeography shows a series of linked basins, coloured in that sort of orangey brown colour, that extend more or less north-south from southern Britain all the way through the Midlands into the North Sea and then the Irish Sea. On the left is a more detailed perspective, a 3D perspective of those basins. The colours on that map, they're shown as elevation. So the blue colours are deep, they're deep basins, minus 3,000 metres to an elevation of plus 500 metres. So you can see that in the south of Britain, the Wessex Basin, the Weald Basin, were deeper centres. There was then a ridge running more or less east-west across from the Mendips into the London Brabant High. And then you move into the Worcester Graben, which is also a deep basin. So one of the questions that we will revisit is, could you possibly have a connection in the Triassic from those southern basins in southern England all the way up into the Midlands and Cheshire and the North Sea and the Irish Sea beyond? So linked basins, but quite how linked they were is not entirely clear. The Worcester Graben clearly fed into the Midland basins, then on into the Cheshire Basin and the Irish Sea.
So pretty much all of the stratigraphy of the Trias is on this slide. And the important points to take here is, if you look on the left, there's the Triassic timescale. The Triassic goes from around 252 to 201 million years ago. And it's divided into an early, middle, and late period. And the Arden Sandstone is in this late period, and it covers the stages, Carnian and Norian. And on that diagram, we've actually shown halites in a red colour, the Arden Sandstone in green, and the background Mercia Mudstone Group, which the halite and the sands occur in, are in that sort of pale greyish colour. So these are all late Triassic in age, and across from the Wessex Basin right through the Worcester Basin into the Midlands, Cheshire Basin, the Irish Sea, and out into the North Sea, there is this sandstone that occurs at the same stratigraphic level. And there are several halite deposits, and they're all enclosed in these red mudstones. And the Arden Sandstone has been referred to as the Carnian pluvial event, which is a very wet period in this late Triassic time. So what we're going to do is look at how the Arden Sandstone is developed and what the enclosing mudstones actually look like. So the question is, what is the Mercia Mudstone Group? Well, as you can see there in the text, it's a thick sequence. In some places it's 1,500, 200 meters thick, a predominantly arid alluvial plain muds with soils flanking saline, which we think were probably acidic, evaporitic lakes. And those lakes contain gypsum and halite. And when you see them at outcrop, there's actually no halite and no evaporites preserved. And why is that? Well, that's because they get dissolved at outcrop. And on the right, there's an experiment done by a lady called Kathy Benson and her researchers. They took some cores of these halite beds and dissolved them, put them in beakers, and let the halite dissolve. And they observed that somewhere between around 50% and 85% of the thickness of the sediment was actually removed during dissolution. So all these sequences we see in the Mercia Mudstone Group at outcrop, they've had all of the evaporites removed. And that's probably the case in all of the outcrops. So part of the depositional sequence, the halites, the evaporites, gypsum and halite, they simply get dissolved. So let me just quickly recap, because that probably didn't make any sense at all. Here's a view of Sidmouth East Cliff with red mudstones, and you can just about make out there are white, very thin layers. And this is the type section of the Mercia Mudstone Group on the south Dorset coast. And the Mercia Mudstone Group is a thick sequence of predominantly alluvial plain muds that contain soils, and they flank what were saline and probably acidic evaporitic lakes. And in those lakes, gypsum and halite precipitated, but you very rarely, in fact, you actually never see those at outcrop, or only see relics of them. And the top right-hand corner of this slide is an experiment done by Kathy Benison and some of her co-workers, and there's a reference down at the bottom. So she actually compared outcrop sequences with core from some places in the USA, and she puts cores of halite sequences into beakers and dissolve the halite. And in those experiments, somewhere between 50% and 85% of the sediment was simply lost in dissolution. So we can speculate that in these evaporitic sequences in the Mercia Mudstone Group, large amounts of the sediment have actually just gone by dissolution at outcrop. So what we see at outcrop isn't the whole story. No, that's not working. Right. So here's an example of the Mercia Mudstone Group in a borehole. And this particular borehole was drilled close to where we are here. It was actually drilled in Solihull, some 10 miles away from here. And they cored 300 meters of the Sidmouth Formation, those we've just seen in that cliff at outcrop, down to the top of the Sherwood Sandstone Group. And lo and behold, in this core, it contained evaporites. It had, in this case, no halite, but it had lots of sulfate. And in the large core photograph in the center, you can actually see a white gypsum nodule and lots of other sedimentary features in this sequence. And we've actually logged this core, and we also took a series of magnetic susceptibility measurements. So we've got two logs here, the sedimentological log, which describes the rock color and the grain size. There's a thin sandstone in the middle of the sequence. And then the magnetic susceptibility measurements down to the core also record some sort of cyclicity. And that cyclicity is present on an amazing scale. In this case, it's only every few meters. And then we've actually run a particular program that looks at the frequency of those changes, and we can see they're very, very high frequency. We'll come back to this type of story. So there is, in these sequences that preserve all the evaporites, there's this regular cyclicity through what otherwise looks like boring hundreds of meters of red mudstone. There is a story in there, and we'll figure out what that tells us. So just to go and look for a modern analog, there are several places around the world. Did that slide move on the presentation?
Yes, yes.
Good. So we're now going across to Western India, a place called the Ranns of Kutch. And if you look on the left-hand map, there's the Gulf of Kambat, and Mumbai is just to the bottom of that diagram. And that's that large projection of land south of the Little Ranns is Saurashtra. So this is Western India. There's a mountain range just off to the right, the Aravalli Hills, and the two dotted red lines demarcate two major faults. So the Ranns of Kutch is a depression on the west coast of India. It's actually protected from the sea, so it's now fresh water. Well, it was inundated in the past. And then the diagram on the top right is a bit more detail of the Ranns of Kutch, and the white areas are salt deposits. You can see the line of the fault across the top of where the salt ends abruptly. So this is a fault-controlled valley with salt precipitating in modern-day lakes. And during the monsoon, rains fall in the Aravalli Hills to the east of the Ranns of Kutch, and this large yellow-coloured alluvial plain deposits sand that floods out and then feeds into these lakes. So these are saline lakes flowing into a rift basin with evaporites forming. And you can stand on the edge of the Saurashtra Hills and look out across those lakes, and that's pretty much what it would be like if you were stood on the Malvern Hills looking into the Worcester Graben and looking at the red Mercia Mudstone flats with saline lakes. And there are the typical mudflats bottom right that develop all around the fringes of the Ranns of Kutch. So for a depositional model for the Mercia Mudstone Group, this is not bad. It's a rift basin with a large sediment input onto one side of it, which flows into the rift basin, and then evaporative lakes form salt and gypsum in the dry season. There's one more good example that's actually been quite well studied, and this is in southeastern Australia. So this is just somewhat east of Perth. There's a large inland arid basin in which a whole host of small shallow evaporative lakes form, and in those lakes, the center of the lake precipitates bedded halite and gypsum, and then on the mudflats out on the flanks of those lakes, in the photograph of Aerodrome Lake, you can see there are wide expanses of mudflats. Halite and gypsum also grow in those mudstones. So these modern analogues of rather muddy sequences, they develop soils, they have mudflats, and in the sediment, halite and gypsum precipitate as digenetic minerals. So that's pretty much what we think the Mercia Mudstone Group was like. Two people I want to mention here. One is Leonard Wills. He first recognizes these sequences in the Mercia Mudstone Group back in the 1950s through to the 1970s and did extraordinary work. And then subsequently, a gentleman called Paul Milroy, did his PhD on the Mercia Mudstone Group and developed some depositional models. And he describes many of the features that we see in these modern evaporatic lake sequences, which are directly comparable to what we see in the Mercia Mudstone Group. So there are desiccation cracks, there are these large TP type structures, contraction structures, And there are sequences of evaporitic nodules, anhydrite, the gypsum nodules, thin sandstones, a typical Mercia Mudstone Group sequence. Is that screen in the way? Yeah, that's got it, right. So let's take a look at some of the outcrops of the Arden Sandstone, having set the scene. So we have Mercia Mudstone Groups, which we recognise as this arid player mudflats in which lakes developed. And on the lake margins, there are soils and thin sandstones flank the lake margins. So let's now go and look at the Arden Sandstone. And I've selected several outcrops from around Worcestershire and Warwickshire, and also the Wiscombe borehole, which is in South Devon, which is an inland version of those cliffs we saw at Sidmouth, to give you some examples. So off we go. So the first one is in Inkbarrow, which is where the arches are recorded, so are allegedly from. So it's a famous location. And this is a roadside outcrop of the Arden Sandstone. And shown on this slide, on the right is my graphic log. These logs need a little bit of explanation. So the central, so there's thickness measured. This column here is the lithology. So the dashes for shales, the dots are the sandstones, and this side here is grain size, with increasing grain size off to the right, and sedimentary structures. So you can see straight away the Inkbarrow section actually is mostly sandstone. There's almost no shale here. When you look at the outcrop, the shales occupy these very thin recesses in the cliff, but this mostly sand. So this is quite an extraordinary package. And this is a sand-dominated sequence of approximately 5 meters that records flash floods introduced into the Mercia Mudstone desert alluvial mudflats. So in the winter, when the vegetation dies back, there's some 250 meters of lateral section exposed. And you can walk along the whole section and you can see that it appears flat bedded. And that's quite extraordinary. So sandstones that are flat bedded in this type of setting require some explanation. You can trace individual beds almost the full length of the outcrop. When you get close up, there are some bed forms, some cross beds, and they're only a few centimeters in height. This is 10 centimeters. So these are quite small bed forms. There's a little bit of incision you can see in the middle slide. And then you can plot on this diagram bottom right is a measure of flow velocity and flow depth for bed form height. And for these sort of bed form heights that we're recording in this outcrop, and you can see actually this is really high energy flow. So just to look at that in a little bit more detail, the top left is an example taken from a small part of the outcrop where you see a transition from parallel plain bedded units into preserved dunes, which then go back into plain beds. So there's this feature called a Froude number, which relates the flow velocity and water depth to the bed type. And when you have very high velocity currents, you actually have standing waves preserved in the package. So these dunes here, you can see the shape of them. They're actually preserving standing waves. And you pass into low angle cross bedding and then into plain beds. And that records a falling Froude number. So that tells us that if the Froude number is less than 1, you get laminar flow. That's the normal sort of flow. If the Froude number is greater than 1, it's turbulent flow. And you have a hydraulic jump when the Froude number is actually at 1. And if you want an example of how to visualize this, if you run water into your bath and the water flows from the tap down to the bottom of the bath, when the water hits the bath, it's usually high velocity and it flows out very quickly. It forms a thin layer of turbulent flow. And if you watch it, as you move away from the turbulent flow, there's a rim of the Froude number of the hydraulic jump when the Froude number is 1, and then it becomes laminar flow. So it's worth trying that in your kitchen sink or in your bath next time you're running some water. You can see that transition. And that's recorded here in the Arden Sandstone. So we're going from really high velocity flow into laminar flow through a Froude number of 1 back into high velocity flow. So we're recording here changes in the water flow rates in the bed forms. So we're probably seeing something like, there's no ripples preserved here, we're going from dunes into upper flow regime plain bed. So this is really high velocity flow. Wow, these were flash floods. So the bed forms in the Arden Sandstone indicate this very high water velocity. That's actually quite unusual. So let's just now jump to, can we tell what direction were the rivers flowing? So this top left is a map of that area. So here's the Inkbarrow Fault. Yeah, that's the Inkbarrow Fault here. The Inkbarrow outcrops is about there, where the little anticline symbol is. And then the other outcrops we're going to look at are over here in the Knoll Basin around Shrewley. So the Licky Ridge is the margin of the Worcester Graben, and this is going out into the Knoll Basin. So this is taken from the British Geological Survey memoir. And here around the Inkbarrow outcrops, you can see the derivation is actually coming from, the flow directions are coming from the southwest towards the northeast. There are much more varied flow directions around Shrewley and Rowington, but in this area around Inkbarrow, those high velocity currents are flowing from the southwest to the northeast. So they're flowing across the map in that direction. So that tells us there was river input in the Inkbarrow area, bringing this high velocity flash flood water into the basin. That's not very visible, is it? Okay, that's interesting. So my diagram on the right-hand side appears to be washed out. I need to revisit that. This is one more outcrop. This is in Henley and Arden. So it's a road cutting on Blackford Hill, which the Warwickshire Geological Conservation Group spent some time earlier this year clearing with the help of Warwickshire Highways Authority. So this is before it was cleared. We've now actually taken off much of this talus and vegetation and have a full section, which I was supposedly showing there on that log. Never mind. What you can see in this outcrop, it's actually quite coarse grained. There are places where you can see these ripper class conglomerates and the sandstones reach medium to coarse grained sandstones. There are some thin crossbeds, which are, again, there's the hammer for scale. These are, again, 10 to 20 centimeters in thickness, so they're quite small scale bed forms. And you can also see that there are some really nice ripples. So there's my overlay. If you follow that line there, there's a layer of ripples, and these actually are almost symmetrical. And when you take these samples and slice them, you can see these small burrows, which are chondrites burrows. So they're probably some sort of worm living in, and they're occurring in the muds. So this environment was not only wet with ripples, but it also had animals living in it. Just a few more examples from this hill cutting outside Henley and Arden. So here's a slab which has got ripple crests on it on the top left, and you can see there are wavy trails running across it, and there's some sort of grazing trail, potentially a gastropod or some crustacean coming out and moving in the shallow water on top of the ripple crests. Top right are some small horizontal burrows. They were first described by John Pollard and Jeff Warrington from Nottinghamshire. These are Planulites montanus. So these are small horizontal burrows, potentially a small crustacean, again living in those waters. Bottom left is this clam shrimp. You can see those small, almost bivalve-shaped shells. And there is concrastration. We'll come back to these in a second, explain more what they are. But they were clearly living in those sediments. Lots of plant fragments. And also in the bottom right there, you can see these large vertical burrows. There's one there running left centre that goes from the top of the slide almost down to the bottom, large burrows. So evidence of life in the Arden Sandstone. There was lots of it, at least when these rivers were flowing. So let's just talk about clam shrimps briefly. What are clam shrimps? So they used to be grouped into this group called Conchostracia, and they're actually freshwater crustaceans. They're not clams at all, they're little crustaceans. They have these small carapace shell, hinge-shaped shells, which they clamp shut when they're disturbed. So they do look a little bit like clams. However, the animal inside is a little shrimp-like creature, which has these flagellae and legs, and it swims around. Now, they're actually quite small. There's a scale. This is the world's largest at 10 millimeters. So these things are not huge. They're not going to eat you. And they're related to water fleas, tadpole shrimps, fairy shrimps, and they live in ephemeral ponds and lakes. Most of the time they spend at the bottom of these water bodies filtering particles, and they frequently burrow into the mud, so they create lots of traces. So lo and behold, the Arden Sandstone was ephemeral. It was full of these Eusteria clam shrimps. So we're starting to build a picture of the sedimentology and the life that was living in it. So nearby Henley, there's a place called Great Owl, and just outside Great Owl, a small village of Spurnel, where a borehole was drilled some time ago by the BGS into this sequence. And I've looked at that core. I've looked at it twice. I looked at it many years ago when I was doing my PhD. And here's my log of it. And the sequence you see there is actually quite different. There are no thick sands that we saw at Inkbarrow. There are lots of mud cracks in the mudstones. There are gypsum. You can see gypsum nodules in parts of the core sequence. There are mud cracks. There are thin sandstones. There's a few very thinly cross-bedded and rippled sandstones. But essentially, this is just a lake margin. So here we are, a mere 5 miles away from Henley and Arden. There's none of the thick sandstones we see that were fluvial at Inkbarrow or at Henley and Arden. This is a lake margin. So the story is starting to build. In places we have sand input, as thick, high-energy fluvial sands that appear to be flood deposits, and in places you just have a lake margin. So someone asked me a little while ago, isn't the Arden Sandstone all the same? Actually, categorically not. It varies hugely over relatively small distances. So I'm now going to make a big jump way down into Dorset again. In this case, just to illustrate some of the variability you see in the lake. And this is one of the best examples of the lake sequence and lake margin I've encountered. So the log on the right shows that the background depositional lithology is the red mudstone. And then interspersed in that red mudstone are several, 1, 2, 3, 4, 5, 6 or 7, very coarse grain. If you can just make out on the grain size, it goes out to coarse and very coarse grained. And there are some examples of that very coarse grained sediment in the core. The one on the left, at 299.5 feet, you can actually see really large clasts. There are several of these rip-up clasts, angular clasts. So these are pieces of the lake margin that were cemented, they're dolomite, that have been ripped up either by wave motion or small currents coming in. And then in the middle of that section, there's a unit that contains some sands. It's 1, 2, 3 meters thick. So there's a small sandstone package in the middle of this sequence of the lake. So this, in the Wessex Basin, I'm not saying it's the same lake as we have in the Midlands, but this is just an example of the type of facies that you see in these lake margins. So they had dolomite forming around the edge of the lake, sulfates, and these dolomites were broken up by wave action or small river currents. Now that Wiscombe Park borehole has actually been studied. I apologise that slides have got cramped. By actually several people, and they've looked at this cyclicity again. So on the right is the section through the Wiscombe Park borehole. There's the mudstone, the Sidmouth mudstone at the base, and at the top is the Arden Sandstone. And they've measured the middle scale is isotopes of carbon from organic matter, and on the right is a calcium titanium ratio. So what you can see in the Sidmouth mudstone, even where there are evaporites, gypsum beds, actually the carbon isotope value is pretty constant. There isn't a huge amount of variation in calcium and titanium. When you get into the Arden Sandstone, there are these huge fluctuations in the isotope composition. They also match other parameters. So there's this cyclicity that's recognized in this Carnian package in the Arden Sandstone. And that cyclicity, it corresponds to 405,000 year cycle, which is related to gravitational interaction between Jupiter and Venus, changing the Earth's orbit. So we have a floating astronomical scale of 405,000 years cyclicity recognized in the Carnian. And what's extraordinary is that this is not just found here in the UK, it's actually found all over the world. So we've gone from looking at lake sediments to recognizing a cyclicity on the scale of 400,000 years. Wow. So let's now just go back into Warwickshire, having recognized that cyclicity, and we're back to the Grand Union Canal. So this is where you saw a photograph right at the beginning of the talk of the Canal and Rivers Trust clearing section. This is how it looked some time ago. So there's a lower section of mudstones, and then you move into thinner bedded sandstones before you encounter a thicker sandstone package. And currently there's around 4 to 4.5 meters of section exposed, the lower 2 meters are mudstone dominated, and then we have a sandstone dominated package. So this looks like a lake margin passing into fluvial sediments. This is the sequence where Reverend Peter Bellinger Brodie collected his dinosaur footprints and fossil fish back in the 1850s, which we'll revisit a bit later in the talk. So a lakeshore face with river channels at the top. Let's just look at a few of those sedimentary features. There's the basal section on the left, the thin bedded sandstones, sharp bases, 10, 20 centimeters thick. When you have fresh surfaces, you can see that there are plain beds, just as we saw in Inkbarrow, and then our rippled horizons. They be passing to climbing ripples. And again, they tell you this is a very high speed current in this sandy unit, passing into with a very high sediment load. More burrows, and in some of the broken slabs, when you look at the upper surface, bottom right, you can see there are these cubic looking structures. They're halite pseudomorphs. So the base of the section was evaporitic. There's our saline lake. It had halite, sodium chloride precipitating. When you go into the sandier bits, we see more burrows, more eutheria, and these high energy flow beds. So we're going from a saline system into what is much, much more akin to a freshwater. And that's a picture taken of the Shrewley Canal last summer. Glorious, glorious evening. But look at the outcrop. So the Warwickshire Geological Conservation Group has some work to do. We'll be there early in 2022, exposing the Arden Sandstone again. If you want to walk, canal side walk, what a delightful place. Just one more quarry we're going to look at. And this is the also on the Grand Union Canal, a few miles from Shrewley. It's at a village called Rowington. It's much the same sequence. So the bottom part of the sequence on the right has those green mudstones with thin sandstones, and then immediately above that is this thick sandstone package. 1, 2, 3, 4. It's 5 meters of sand, and that photograph in the middle shows a 3 meter scale with that sand package in the middle. So it's just again a thick package of sand. And this is the largest channel I've encountered so far. You look at my log on the right, the upper sand, there's a 0.7 meter single sand package. Now that tells you the water depth was, in this case, was at least 0.7 of a meter thick, because that's the bed form that was under the water. So wow, these were, when the rivers were flowing, these were big river events. Right, so now I've talked you through some of the outcrops in the Midlands. Let's just look at what Prof. Leonard Wills managed to get out of the outcrops when he looked at. And this work was done back in the 1950s through to the 70s. It's stunning stuff, and Leonard Wills is one of my heroes. He's really the father of paleogeography. So amongst several other things, one of the great things Leonard did was reconstruct the geology in the past and the past environments. And the map on the left here is his figure 15 from his 1970 publication, which is a Geological of London article. And the colours show, the brown colours on the bottom right and bottom left and in the middle are the uplands. This one on the bottom right is the London platform. On the bottom left is the Welsh uplands. Then in the north there's the Pennine uplands. And the red lines are the main faults. So in the centre, left centre is the Worcester Graben, which extends into the Midlands basins. And there's the South Staffordshire coalfield, and then the Coventry coalfield on the right. And between those highs, the uplands and the coalfields, which are also upstanding horse, are these sedimentary basins. And the sort of greeny colour flanking those are areas where we think there were thin deposits. Wills thought there were thin deposits of Mercia Mudstone Group, but only in the grabens, in the basins, where the faults down throw to create the depressions, do you have thick sequences. The pinky colours are the halite deposits. So there's a big halite deposit in Cheshire, still mined. Winsford mine is still open. There's an old area in Stafford that was mined at one point. And there's a halite in the Needwood Basin, and then down here around Droitwich and further south. So they're halite deposits, which are more or less contemporary with the Arden Sandstone. And the blue colours are lakes which Wills had gypsum precipitating it. I'm not saying they were all exactly contemporary, because you have to remember that the Carnian covers around 10 million years. But at some point in the Carnian, there was an Arden Sandstone lake, and then these halite and gypsum lakes in these depressions. And they occupy the basins between the highs. And the Arden Sandstone, this is Will's map of the extent of the Arden Sandstone. It goes all the way from Newnham on the Bristol Channel margins, right across the Worcester Graben, into the Knoll Basin and around where we are in Warwickshire. There's a fault in the centre where it says Sandstone Lake is the Inkbarrow fault system. So it looks like we were introducing fast-flowing waters from the southwest into this lake basin, and also around Rowington and Warrington. So there's a sort of paleogeographic reconstruction of lakes, some precipitating halite, others depositing sandstones in the Mercia Mudstone Group. We do know from more recent boreholes that the lake probably extends a bit further south, down towards this high in the far south, Mendip Bruton Ridge. So we think the lake probably extended a bit further south. So we've now reconstructed what the distribution of sediments was in the late Triassic within these sedimentary basins. And Wills was doing this, bless him, back in the 1950s. It's really quite extraordinary. And we know from the work we're doing now, his maps are pretty accurate. He wasn't that far off. And Leonard, he retired in 1949, but was still publishing in 1976. What a man. So what does this all mean? I've taken here two diagrams from a gentleman called Tom McKee, and he published this in 2014. And this is taken from an equivalent sequence in the North Sea, in the central North Sea. But I think his interpretations are pretty spot on. So he has both diagrams, they're similar. Tom McKee has river systems draining low-lying uplands across low-lying alluvial plains onto terminal splays on the edge of a player lake, and these terminal splays drying out. When they were in flood, you have major river systems, like we saw at Inkbarrow, and these were quite high energy. So this I think is a good model for the Arden Sandstone. Player lakes with halites and gypsum terminal splays when the rivers were drying out into the lake margins, and then during flood stages, very high upper flow regime flow into the basin. So the Arden Sandstone records progradation of inland lakes and players and deposition of sandy lake margin deposits during the Carnian pluvial event. These were fed by really fast-flowing ephemeral rivers as flash floods, as we saw at Rowington and Inkbarrow, which now record the deposits of small lake deltas. Clam shrimps, known today from ephemeral freshwater ponds and lakes, fed on algal mats in the temporary ponds and were in turn eaten by Triassic amphibians and reptiles that wandered the lake shorelines. Fish thrived in the shallow lakes, and Crurotarsans, recursive crocodiles, ate the crustaceans and fish. So there's a picture of Arden Sandstone paleogeography and environment. Let's just quickly visit Peter Brodie. So another one of my heroes, who was the rector here in Rowington, in Warwickshire, and he was president of the Geological Society of London. So Brodie is buried here in Rowington Church. His grave is actually just outside the church in front of it. He has this rather fine stained glass memorial window dedicated to him that was installed in 1899. And there's his gravestone, and there's his bust in Warrington Museum. So what Brodie did back in the 1850s was visit these outcrops of the Arden Sandstone, and he made a pretty good log on the right there. There's his section of the Kuiper at Shrewley. Remember, in the old terminology, the upper Kuiper is what we now call the Mercia Mudstone Group. So you can see his lower shales, and then he's got these are actually sandstone packages above them, and that's pretty much what we see today. And in his log is recorded where he's found. Well, he's recorded the lithology on the right, and then his fossil remains, which there is teeth, Euotheria, fish and labyrinthodon reptile remnants. So hand-like impressions of this Chirotherium, one of these predatory reptiles related to crocodiles, fossil fish from this outcrop, and more footprints. So there's a whole story of crocodiles, fish living in this lake when the fresh water came in, as well as Euotheria. So let's just quickly look at how this relates to dinosaur evolution. In the early Triassic through to the Carnian, virtually all of these tetrapods, all of these reptiles and amphibians were these Crurotarsans, the early crocodiles. And then a relatively short time later, there's a complete evolution away from the early crocodiles into true dinosauria. And that evolution change took very, very quickly around the Carnian-Norian boundary. And that's not just the case here in Warwickshire, it's also true all around the globe. North America, China, that example of when I looked at these footprints in Warwick Museum a little while ago, I was amazed just how small they are. So there's one of these beautifully preserved tetrapods from China. They're tiny things, but they're stunning preservation. So what actually drove these evolutionary trends? So we're now going into the realms of serious speculation. So we recognize this cyclicity earlier on. Down in the Mercia Mudstone sequence before the Carnian, very little change. Once you got into the Carnian and the Mercia, the Arden Sandstone, you see changes in all sorts of parameters, TOC, and the changes are very rapid and consistent and recognizable all over the place. So these climate changes they actually characterize the Carnian world, and lots of people have speculated that they coincide with a huge outpouring of basalts in northern North America and in the central Atlantic province along the Newark, eastern USA, down into Morocco and central Pangaea. And the Rangalia basalts, there's 3 kilometers of flood basalts that were erupted in the Carnian. So one speculation is that this global volcanism, and this map on the top left is of the Carnian world, and the green colours are the active igneous provinces. So on the left there is number 1 is Rangalia, one in the middle of Pangaea is the Central Atlantic Magmatic Province. There's one up there in Siberia, and then a whole bunch of volcanoes just to the east of the Pangaea supercontinent. So was it the initial breaking up of Pangaea and volcanism that caused this sudden change in dinosaurs? Well, where do you go for the answer? The Daily Mail. Waves of volcanic activity triggered the dawn of the dinosaurs and ended the Earth's Triassic period. Well, if the Daily Mail says volcanic activity triggered the dawn of the dinosaurs, it must be true. So we're going to wrap up now. On a pleasant sunny day, you can gently wander along the banks of the Grand Union Canal, visit these important outcrops, trace the Reverend Brodie's footsteps, imagine the torrential flooding of the Carnian Desert, envisage blooms of clam shrimps in ephemeral pools, and envisage the dawn of the dinosaurs in the green sediments of the Arden Sandstone. There you go. We've gone from local geology, leading edge new science, nice photographs, canal side walks, dinosaurs, a local hero to volcanoes and climate change, the Arden Sandstone. Thank you.